right, good morning, ladies and gentlemen. Let's get started. So just a reminder to please fill out the lecture capture survey that's on the course link site for this course. This will be the last week it's up, so please get your opinions heard, whether you use the tool or you don't use the tool. I want to know all about it. Okay, so on Friday, I guess it was, we got to thinking about regulating the respiratory system, and we're going to go through 3 examples to flex a little bit of muscle in terms of regulating the system, thinking about, so what we're going to be doing is whipping around that negative feedback loop. We're going to perturb the system in some way. So we're going to have sensors sense oxygen and CO2 being perturbed, and then there's going to be that information is going to go up to the coordinating center, and then we're going to get information coming out to the diaphragm and the intercostal muscles as effectors, which are going to change frequency and depth of breathing to change or to hopefully restore our CO2 and oxygen back to normal. Okay, so that's essentially what we're going to be doing during these 3 examples. And like I said on Friday, these are data from a computer program that simulates a human and its responses. We started an example of increasing your dead space, so essentially just putting a snorkel in your mouth and how that is going to change your oxygen and your CO2 and how your body's going to respond to that. So key to using all these kinds of, or key to solving these kinds of problems, whether it be one problem, like the respiratory system, which is going to mess up 2 things, oxygen and CO2, but also when we're solving big problems is to try to figure out how the body was perturbed. Because if the body wasn't perturbed in any way, then it's not going to respond, right? Because the body is built, what we've done up to in the course so far is showing you that we have sensors for specific things, and when you get those things out of whack, the sensors sense them, and the body is wired in a way to respond. All right, we've been working really hard in the first 6 weeks of this course thinking about mean arterial pressure and how the body is wired to respond to changes in mean arterial pressure. Well, if you perturb a system and it doesn't get mean arterial pressure out of range, then the body isn't going to respond that way. Okay, so the key is to try to figure out how did this, whatever we did, provoke the body to change one of the regulated variables. All right, because if we don't have sensors for it, the body doesn't care. The body doesn't care if that thing got out of whack. Okay? So we were messing with dead space, putting a snorkel in our mouth. What did that actually mean? That actually meant that in essence, our alveolar ventilation went down in terms of the new air that came in. Okay, so then we would look at, a drop. What we have essentially here is a drop in alveolar ventilation because we have more dead space, right? So we're bringing in air that's already been pre-equilibrated. Okay, so we're bringing in air that's already been at the alveolus. It's already exchanged its oxygen and unloaded CO2. Okay? So then how would this, what we have to do now is try to predict how this would change oxygen and CO2. Because if it doesn't, we can just take this away and move on to the next question. Okay? So what would you do in order to predict how this drop in ventilation would affect oxygen or CO2? What would you do? How would you be able to find out whether a ventilation change altered oxygen or CO2? Yeah. So we need to find the partial pressures in the systemic arteries. Brilliant, right? Because that's where we have the sensors, right? And so how were we predicting what the oxygen and the CO2 were in the systemic arteries? Perfect. So we were using alveolar oxygen and CO2, and how were we predicting that? We were using the VA over Q ratio. Okay, so we built a tool whereby we compared VA over Q and how changes in ventilation and changes in flow altered oxygen and CO2. Okay, the relationship looked something like this in terms of PO2, PCO2, normal VA over Q ratio was hanging out around here somewhere. And then we had a comparison of what happened when the ratio got really big or what happened when the ratio got really small. Okay, so remember this tool. So we have a drop in ventilation, all right, which means our numerator is getting very small, which means our ratio is getting very small. Okay, so our ratio is tending towards 0. So we can just read it off the graph now. This would cause a drop in oxygen and an increase in CO2. That's exactly what we should expect. Okay, so from here we should see a decrease in PaO2 and an increase in PaCO2, right? So we could predict what was in the alveolus, and we knew that we equilibrated with that, and then that's what's going to show up in our blood, okay? So indeed, if we start thinking about our problem here, and then move to seeing what would be happening with PaO2, boom, there it is. We would have predicted it would have dropped. There it is. And our PaCO2 goes up. So there's that graph, that representation. Okay, so our predictions were completely spot on, okay, using that tool. I also have an indicator of, as we talked about on Friday, an indicator of hydrogen ion here, because we know now, based on how we carry oxygen and CO2 in the blood, that CO2 and hydrogen ion are intimately related. So if we had CO2, and that's through carbonic acid, right, so based on this relationship that we know is happening right in the blood, right, it's happening in the red blood cell, but it's also happening in the plasma. So if we get a change in PO2, or sorry, PCO2, right, that's in the dissolved plasma portion, then we're going to combine it with water and make hydrogen ion. Okay, so an increase in PaCO2, right, and this is just going to be mass action now, an increase in our substrates are going to push the equation in this direction, so we get an increase in our products. Okay, so an increase in CO2 in the dissolved space in the plasma is going to cause an increase in hydrogen ion. Okay? So indeed, an increase in hydrogen ion, we're going to get ourselves a drop in pH. Okay, so that's how the body is then provoked by putting this snorkel in your mouth. Okay? So we will equilibrate our alveolar oxygen and CO2 into the blood, right? So we're going to have a drop in oxygen in the systemic arteries and an increase in CO2 in the systemic arteries, and that's about to then flow by our sensors in the aorta and in the carotid arteries, okay? We're going to change their frequency up into the coordinating center and back down to the diaphragm to change ventilation in order to rectify this problem, okay? So how would the body then respond? Let's pick on one, because there's two sensors we have to visit when it comes to respiration. How would the body respond to a decrease in oxygen? So think about those sensors that we looked at. Okay, what did the relationship look like between PO2 and ventilation? Think about that relationship, because that relationship tells us how the body's going to respond to a drop in oxygen. So Drop in oxygen, what happens with ventilation? Anybody got it? Perfect. So we go with that funny relationship that looked like that. Perfect. So indeed, if we were to drop oxygen, we would expect ventilation to go up. And indeed, if we looked at ventilation, what am I at? I'm number 1, 2, 3, 4, I'm at 5. Right? If we looked at ventilation, minute ventilation, so breaths per minute or liters per minute, right? Ventilation goes up. I guess we were looking at a smaller example. Right? And then we know that ventilation was a product of our tidal volume times our ventilation frequency. Right, so how deep you were breathing, 500 mils versus 800 mils, how much air you're bringing in there, versus frequency 12 times per minute versus 15 times per minute. We talked about these sensors didn't actually choose one strategy over the other, right? That we actually saw it chose a combination of both, and indeed, these data prove that if we look at our tidal volume is going up, and our frequency of breathing is going up. So the body chose to do a little bit of both in order to increase our the amount of volume we brought in per minute. Okay, so the body didn't choose one strategy over the other. Okay, so that's again just us moving around that negative feedback loop. Okay, we had sensors that sensed it. Send information up to the coordinating center, contracting the diaphragm harder. Okay, the contraction was more forceful. That's how we got more volume in, and it happened more times per minute. Okay, and in fact, you know a lot of information about how this got into the coordinating center, right? You know that these chemoreceptors went straight into our central pattern generator at A. And that's where it managed to change both force of contraction and frequency of the depolarization, okay? So relate that information to where we are here. Okay, so the PO2 sensor pans out. What then is happening with CO2? Because we had another problem here too. CO2 is going up. Alveolar CO2 is going up. What does that mean? So we've got a CO2 sensor, and what does that do to ventilation? So again, think about the relationship between CO2 and ventilation and what that looked like, because that's going to tell us how the body's going to respond to this provocation. Okay, so what's going to happen here? Increased CO2, what does this relationship look like? Are we going to increase or decrease ventilation? You got a 50-50 shot if you guess. Yes. Increase ventilation. Perfect. Right. Because the relationship looks like this, right? We live here, and we increase CO2, and we increase ventilation. Okay? So both sensors are bringing information into the coordinating center, into A, and causing the same thing to happen. Okay? So the body then would be in complete agreement over what was about to happen, increase ventilation, increase tidal volume, and then you can actually see that we start to fix the problem. So if we look over time, you can see our oxygen gets restored back to normal, our CO2 gets restored back to normal. Okay, so we're starting to fix our problem. Excellent. So good news is you can put a snorkel in your mouth and things will be fine. As long as it's not that 12-foot snorkel, you'll be good. Okay, so can you see how the tools that we're going to pull out and the thinking we're going to pull out in order to try to solve ventilation problems? Okay. All right, let's do another one. Let's go with high inspired CO2. So we're going to trick the whole system here and increase inspired CO2. So we have essentially 0% CO2 in the air that you're normally breathing in, and suddenly you're in a room where we've raised that to 5, okay? The 5% CO2, we're going to deal with this first. 5% CO2 free ventilation is what that says, okay? We'll work on the fixed ventilation in a minute, but let's think about then the free ventilation. So then how is the body perturbed here? How would you work your way through that? Increased inspired CO2. What's that going to change about anything? Okay, so if it doesn't change anything, then we can move on to the next one because the body isn't going to be changed. Okay? How would the body be changed by increased inspired CO2? Yes. So we would increase ventilation. Okay, so take us through how you got there, because you went straight from, you knew what the problem was, you went past the sensors, and then you changed ventilation, and boom, you've got the answer. Okay, so let's take us through those individual steps. Okay, so what changed about something the body cares about, either oxygen and CO2, with this problem? So can you tell me how you got there? So you're talking about chemoreceptors? Yeah, so they're on the systemic side, so they're in the aorta and the carotid arteries. So this is why we need to take the steps, because we need oxygen or CO2 to change in the systemic arteries. So how did increased inspired CO2 change oxygen or CO2 in the systemic arteries? You increased hydrogen ion concentration. We will do that too, right? But that's an effect of the change in CO2. So you're just missing, what's the connector? How do we change oxygen or CO2 in the blood? So we'd be decreasing ventilation, but remember, if we're going to decrease ventilation, we had to have perturbed the body to do that, right? So how do you change CO2 in the blood? You have to change alveolar CO2, right? That's the compartment that we are equilibrating with, right? So the question here then would be, did alveolar CO2 change when we increased inspired CO2? Yes. Okay, so if we breathe in more CO2, we are breathing in more CO2, right? So that's the challenge to the body. We now have more CO2 in the alveolar space than we did before. So if we've got more CO2 in the alveolar space, then we have more CO2 in the blood. Okay, so that's that connection. Okay, and if we've got more CO2 in the blood by those sensors, then boom, we're going to get the changes in ventilation you're after. Okay, so we'll just take it step by step. So you're absolutely right in what you were saying, except you jumped to the answer. But let's just think then about the process one at a time. So indeed, we're going with the little black boxes here. We would expect to see alveolar CO2 go up because we're breathing more in. We were breathing in 0%, now we're breathing in 5%. Alveolar CO2 goes up, okay? So we start here, and then indeed we're going to get a change in hydrogen ion based on that. So if we think about our carbonic acid relationship, right? If I were to increase my CO2. I'm going to increase my dissolved CO2. So I'm going to increase that. And I'm going to push the equation in this direction, just straight mass action. So I'm going to increase hydrogen ion, decrease pH. Okay, so that graph makes sense. Okay, so we've got an increase now in CO2 in the systemic bloodstream. Okay, we're about to then pass that by sensors in the aorta and the carotid arteries. So then what is going to happen to ventilation based on an increase in CO2? Increases, perfect. Right, because of that relationship, right, we live here, we're going to go up. Right, so an increase in CO2 will cause an increase in ventilation. So indeed, where's my ventilation graph here? 1, 2, 3. So we've got an increase in our tidal volume and an increase in our frequency. Okay, so there we are, contracting the diaphragm harder. So instead of 500 mils, we're bringing in more. And we're contracting more often. Instead of 12 times per minute, we're doing it more often. Wow, up to 25, that's a lot. Okay, cool. So when we look at fixing our problem, we actually don't see that we fixed the problem, right? So this is because the problem is in the air. The body can't fix that problem, right? So when it actually breathes in more, it's breathing in more CO2. Okay? The body, so this is just show you that the body has no idea where the problem is. All it knows is it has a sensor in the aorta, and when there's a change in CO2 that goes by it, it's wired to respond this way. It has no idea where that CO2 is coming from. It's just going to respond that way. Okay? So in this case, we can't actually fix a problem. The body responds in the way that it should. It can't actually entirely fix the problem, though, because it's an atmospheric problem, and our body isn't built to fix that problem. Okay? So indeed, 1, 2, 3, 4. So why then, if we look at our PO2, why did our PO2 go up? Why did our alveolar PO2 go up? We only changed atmospheric CO2. Why did PO2 go up? Why did that happen? Because we increased ventilation, right? So this is also important to remember that when you mess with one, you're going to mess with the other. Okay, you can't change one independent of the other, because changing ventilation will mess with oxygen and CO2. So indeed, we get ourselves to what we did, right, was to increase ventilation to fix this problem, right? And when we think about our VA over Q relationship, we increased ventilation to fix the CO2 problem, right? Why did that work? Increasing the ventilation increases our numerator. The ratio gets really big. We tend towards infinity. So increasing ventilation should drop our CO2. Okay, that's why the body is wired this way. There was an increase in CO2. Let's increase ventilation to drop CO2. That was the whole reason for the maneuver. But there are two gases that are affected by ventilation, so this maneuver is also going to increase our PO2. Okay, how would our body respond to the increase in PO2? Right, so we live here, and we're headed up that way. So an increase in PO2 is not going to change ventilation very much, okay? Because we're not sensitive to high, so that this relationship, the shape of this relationship is critical. It tells us we're not sensitive to high oxygen. We're sensitive to low oxygen, but we're not sensitive to high, right? We live on a flatter part of the curve, not very sensitive, and especially not sensitive to the notion of PO2 going up. Definitely sensitive if PO2 goes down. Very different from our CO2 sensitivity. CO2 changes a little bit in either direction, and we're breathing all over the place, okay? So 1, 2, 3, 4, and then we thought about here, and then we went up to here, just to retrace our steps in terms of this argument. Okay, cool. So we can't fix the problem. We can see how the body would respond, but we can't fix the problem because the problem is in atmospheric air. But in order to see the effect of ventilation and how bad things could have gotten, we look at the second example here, fixed ventilation. So now it's a super bad day. Not only is there 5% oxygen in the air, you're on a ventilator and we fixed it so that you can't breathe more than 12 times per minute and you can't breathe more than 500 mils per breath. Okay, so what we've done is we've taken away the body's ability to try to fix this problem through ventilation. Okay, so if we take away that tool, then you can see how bad life gets. Okay, CO2 goes way off the charts in terms of just going up and up and up in the alveolar space. Is going to then go up and up and up in the blood space. Okay, our pH is going to start to drop. Okay? This is a super bad situation. So you can actually see that although we couldn't fix a problem necessarily, we definitely minimized how bad the problem got. Okay, so ventilation went up to a degree to minimize the disturbance. So that's what respiration is good at. Respiration is really good at minimizing a disturbance until the problem is fixed by something else. Okay? Okay, so ventilation is really good at minimizing a disturbance, and now you can see the level of disturbance that was actually minimized here because CO2 was definitely continuing to go up and up and up. Okay? So we didn't fix the problem, but we got the body stable so that the problem is not getting any worse. Okay? Sometimes stabilization is the best you can do, especially in a situation like this where it's coming from room air. Okay, any questions on inspired CO2? We'll do one more example. We'll go to altitude, see what's going on up there, because we're definitely messing with oxygen and CO2 up there. So, you head to altitude. This is where physiology road trips would be awesome. We could actually go try this out, but in Guelph we can't really get somewhere very quickly. So there are some examples here like, well, let's first of all think about what the problem at altitude is. So when you go up high, so let's go to 10,000 feet. What is going to perturb the body at 10,000 feet? What in terms of oxygen and CO2? Yeah. Atmospheric pressure. So atmospheric pressure drops, right, from 760 millimeters of mercury down as we go up. Okay? So that is super true. So as we go, we start at sea level, and we go up from there. Okay, and we think about pressure in the atmosphere. This would be in millimeters of mercury. All right. We start at 760, so that's been where we've been living around Guelph. And as you go up, atmospheric pressure goes down. Okay, so what does that mean? Our body has no atmospheric pressure sensor. What does that actually mean in terms of provoking the body. Yeah. Perfect. So because oxygen is a partial pressure of that, we've been dealing with 20% or 21% of 760 millimeters of mercury, right, is what we've been dealing with here. But suddenly if you drop that, if you drop partial pressure or you drop atmospheric pressure by half, then you drop the partial pressure of oxygen by half. Okay, so if we were to look at a second axis to look at the partial pressure of oxygen as a percentage of that, then it's going to drop as well. So going to altitude is essentially a decreased inspired oxygen problem. Okay? So we're decreasing inspired oxygen. So we've got 3 measures here. The top one here, an atmospheric pressure of about 500 millimeters of mercury. So this is Mexico City. Very cool experiment done it was to have the Olympics at Mexico City. So if you look at the Mexico City Olympic records, weird and crazy things happened because suddenly they took a bunch of athletes and took them to altitude and then let them do whatever it is that they do, whether they throw a ball or kick a ball or jump over a rope or jump over a bar or whatever they did. Weird stuff happened. So lots of weird things happen when you take weird people, because I call it what it is. Olympic athletes are absolutely built for, they're physiologically chosen for like the one thing, right? They're physiologically elite in doing this, right? They can push a shot put, and they are the best in the world at that. So they are weird physiologies. They're extreme physiologies, and when you take an extreme physiology and put it into a weird environment, weird and wonderful things happen. The second one here is Pikes Peak. That's in Colorado. That's on here because Pikes Peak is it's about 14,000 feet, and you can drive up to it in about half an hour. So you can get yourself from about sea level to 14,000 feet in about half an hour, which is all kinds of physiological fun, right? You take yourself to altitude in that period of time. Myself, when I went up, not really thinking much about my CO2 and my oxygen. We drove up, and I was getting a little bit of a headache as we went up, but that's fine. I can get over that. Got up to the top of Pikes Peak, and I'm excited about mountains and all that kind of stuff, and get out of the car, and I run around to my husband's side of the car, and I collapse on the floor, on the ground, right? And then spend the next half hour slowly trying to crawl my way to the little restaurant they have up there to just try to get a drink and desperately get down, right? Because the level of oxygen up there just not remotely ready to deal with the low levels of oxygen that are up there and what my body was about to do with those low levels of oxygen. So because you can get up there quick, no acclimatization, it's gonna totally mess with you. So I would highly recommend taking a trip to Pikes Peak if you can and mess with your physiology. It's all kinds of fun. The third one here is Mount Everest. Indeed, if you go up to Mount Everest without oxygen, there have been folks that have been able to climb Mount Everest without supplemental oxygen. I have no idea what kind of physiologies these are. I've read books about them. They're absolutely frightening about how these people operate up at altitude. I'm not sure they're operating really at all. But most of the time here, you're going to lose consciousness around this point. Most folks would lose consciousness while they're going up to Mount Everest if they're not taking on supplemental oxygen with them. So don't try that. It's terrible. It's awful. Don't do that. Okay, so we'll think about Pikes Peak. Here we'll think about those data. So what happens with your body? How does your body respond to this decrease in inspired oxygen? Now let's think about what would be how would your body would be provoked by that? Okay, because unless it's going to change oxygen to CO2 in the blood, the body doesn't care. So, what's going to happen? Read it right off the graph. Decrease alveolar O2. Perfect, because we're bringing less in. Brilliant. So there we go. So that's our challenge. Decrease alveolar PO2. Cool. So how would we respond to that? Decrease alveolar PO2. We got a sensor for that? Yeah. We're going to increase ventilation, so we're going to hit our sensor for PO2. Right, and it looks something like this. And then boom, we are stressing that system, so we should fully expect to see, I'll back that up. We increase ventilation. So that's 1, 2, where are we? So 2, yes, we increased our tidal volume. There it is. We increase our frequency. There it is. So we increase our alveolar ventilation. Boom. There it is. And indeed, we would start to then stabilize our oxygen levels. Okay? But what is happening to CO2? What is going on there? Why is CO2 dropping? There was no problem with CO2 in the air, right? Because we're 0% CO2 at sea level, and now we're 0% CO2 at altitude. So what happened there? So there, but it's 0% here. So now there's 0% at altitude. We did. We increased ventilation. Absolutely. So if we increase ventilation, what did that maneuver do? Right? We came in here and we increased ventilation because that was an awesome idea, because oxygen was low. Brilliant. Why did we do that? So if we think about infinity versus 0, we increase ventilation, so our ratio is getting really big, so this should increase our PO2. Excellent, that's why we did it. That's why the body was rigged to do this, right? But that also meant we decreased PaCO2, right? That's exactly what's happening. There it is. And if we decrease our CO2, we could predict what would be happening with hydrogen ion. Okay, if I were to decrease CO2 in the plasma, get this mass action, we would to pull it in this direction. So I would decrease hydrogen ion and increase pH. Call that 5A and 5B down here, because they're related. All right, so what's going to happen as a result of that increase in CO2? An increase in CO2 in the body now, how is that going to affect ventilation? How's that going to change ventilation? Decrease in CO2. Wait. Yeah, we have a decrease in CO2. Yeah. So how is that decrease in CO2? Decrease CO2. How is that decrease in CO2 going to change ventilation? What's it going to do? It's going to decrease ventilation. Dang, that's terrible. Absolutely it's going to decrease ventilation, right? So you got to remember, that there are two bosses here. We always got to look out for one when we change the other. Okay, we cannot change oxygen without changing CO2. So here's the problem. We absolutely do now need to decrease ventilation, right? And we are much more sensitive to CO2s, right? This is what's getting us entirely messed up. All of those feelings that you feel when you go to altitude is because your pH is off, right? So you need to increase ventilation to help with your oxygen, but you got to drop your ventilation now that you increased your ventilation. So your body actually provoked a second problem, right? Your body was doing a great job at fixing the oxygen problem, but the change in ventilation went ahead and provoked a secondary problem, right? So that increase in ventilation that's required here is now promoting a second problem, and we need to decrease ventilation. So what we'll find is that oxygen, or that frequency and tidal volume, and essentially then alveolar ventilation, it didn't go up as high as it should to fix a CO2 problem, or to fix the oxygen problem. And it didn't go down as low as it should to fix the new CO2 problem. It was somewhere in between. So it stabilized the body. Okay, so we're starting to stabilize here. We stabilized the body, but fixed nothing, right? We're minimizing the disturbance here, okay? And why is that? These are just sensors sending in an action potential frequency to change the membrane potential of our central pattern generator. So our central pattern generator is getting stimulatory information and inhibitory information, and that it is just then settling on a frequency and a pattern, or a frequency and a depth of breathing, right? That will satisfy none, but not make the problems any worse than they are. Okay, so now when you're at altitude, you are not breathing as high as you should to fix your oxygen problem, so you're not feeling good. You've got low oxygen. But because you're breathing higher, your CO2 and now pH is off. Okay, so you're going to suppress your breathing in order to bring that back down, but you can't. So now it's like a battle between the two sensors. Okay, but you just get input from both, and the end result is I get a ventilation, I get a frequency and a tidal volume that's going to fix neither, but it's going to stabilize you. Okay, so you go up to Pikes Peak and you sit there, you will not die. You're not going to feel good, but you're not going to die. All right, so ventilation helped stabilize you. It helped minimize the disturbance until something else came along to fix this problem. Okay, fixing this problem requires you be able to carry more oxygen in your blood. All right, so fixing this requires you be able to extract more of that little bit of oxygen that's out in that air, right? So we need more hemoglobin. And that's going to take about a week to 2 weeks to be able to to increase your hematocrit enough. As soon as you start to increase your blood carrying capacity, right, your ventilation will come down because you'll be carrying more oxygen. And as soon as your ventilation comes down, you stop making your secondary problem, the CO2 problem. Okay, but that's why it takes you about 2 weeks to acclimatize, they call it. So you're acclimatizing because you're building more hemoglobin and able to carry more oxygen. So you stop your increase in respiration, and that stops your second problem from occurring. Okay? So we've seen cases then in our examples today where both sensors are telling the body to head into one direction. Okay, and then we've also seen examples where both sensors are kind of are at odds with each other. Okay? Obviously, one isn't going to supersede the other. You're going to come up with a happy medium to try to minimize the disturbance to keep you alive. Okay? Obviously, if we breathed enough to satisfy the oxygen sensor, you would die from hydrogen ion exposure. Okay? If you were to breathe low enough to satisfy that the hydrogen ion problem, you will not get enough oxygen on board. Okay? So it's a happy medium between both. So at the end of the day, you're not going to feel good at altitude for 2 weeks, and then you're good to go. All right, are there any questions there? We will revisit altitude again one more time when we start to look at things over a longer time frame. So at the moment, we're just thinking about ventilation, and we're looking at fixing a problem over minutes, or what would the response be over minutes. Once we get into acid-base physiology, we're going to add the kidney on and think about how we might regulate things over days. Okay? So we're good with altitude? You happy with that? It's fun at Pikes Peak. You should go if you can. Drive up as fast as you can, though. It's super awesome. Okay, good. All right, so that's it then for the respiratory section. What we're going to do now is start the integration section. And we're going to start by integrating respiration and the kidney. So we're going to start integrating 2 systems now to try to help us figure out how we regulate hydrogen ion. So let's take a break then for about 5-10 minutes before we start that. All right, ladies and gentlemen, let's get back to regulating hydrogen ion. Okay, so in this regulation of hydrogen ion section, it's a combination of so obviously if we're regulating hydrogen ion, we've already seen through the this hydrogen ion CO2 equation, right, who the major players are going to be, right? So if we're going to regulate this now, right, we can already see that one of the major players is going to be our respiratory system, because we can change CO2 to help hide hydrogen ion, right? And that's a critical piece here. If you change CO2 in this system, you can take a hydrogen ion, and when you pull in this direction, pull the equation in this direction, and I've been kind of saying that rather cavalierly, what we're doing with hydrogen ion is hiding it in water. We can't get rid of hydrogen ion at the level of the lung. We can take that hydrogen ion and hide it, but we can handle water. Free hydrogen ion, we can't. And then in the kidney section, we did introduce and kind of glaze over quickly all of the tools at the level of the tubule in the nephron that could handle bicarb and hydrogen ion itself. Okay, so we're going to be combining what the lung can do and what the kidney is going to do. So we're going to combine those 2 systems, integrate those 2 systems to see how we regulate a hydrogen ion. So at the end of the day, massive zoom. It's free hydrogen ion that we are regulating, not total. Okay, this is critical because if the body isn't too concerned over total, then we can do tricks like buffer stuff, right? I can take hydrogen ion, bind it to something, hide it there, because the body is not too concerned over total hydrogen ion. It's concerned over that free hydrogen ion. So if the game afoot is we could tie it up somewhere else, then we can help ourselves with this problem, okay? So, and that will be a strategy of the body. At the end of the day, we are hugely vulnerable to hydrogen ion, okay? So in terms of a pH range, the body tries to keep itself at a pH of 7.4, so that's our kind of homeostatic set point, right? And we're okay with 7.35 to 7.45. Okay, so the body is happy if it can get itself back into that range, it'll stop regulating, okay? If pH goes up to 8, okay, you will die. So death will result at a pH of 8. you get yourself to a pH, a whole body pH now we're talking about is 6.9. We go down. You will also die. Okay, we cannot handle a very wide pH range. And this gets particularly concerning then if you look at what this means in terms of hydrogen ion concentration. So we're trying to regulate ourselves around 40 nanomolar. Okay, we're 10 to the minus 9 is the concentration we need to regulate ourselves around. 10 to the minus 9. Okay? If our pH were to go down, which means our hydrogen ion goes up to 125 nanomolar, okay, so not even a 10-fold increase. Free hydrogen ion, that'll result in a nervous system shutdown and death. So super bad day. So when our pH goes up, so we're very sensitive to too much hydrogen ion. We're also very sensitive to too little hydrogen ion, right? So when our pH goes up, our hydrogen ion goes down, but just down to 10 nanomolar. Okay, so very small drops in free hydrogen ion concentration. You're going to get nervous system hyperactivity. And death. Okay, so we are wicked sensitive here. And the thinking is that a free hydrogen ion, if we look at the high level, so free hydrogen ion can bind to things that have negative charges, right? And remember that a lot of what we talk about when we talk about changing action potential frequency and pattern, or generating an action potential that involved a voltage-gated sodium channel, all of those things were dependent on a protein and the shape of that protein, right? Remember we talked about voltage-gated sodium channels, and they're open, inactive, and closed state. Those were all three conformations of that protein, right? So if you start randomly binding hydrogen ions to things that have positive charges, you will change their ability to change shape, right? So that's why if you have too many hydrogen ions and they are binding to proteins, then these proteins can now no longer work. There'll be a lot of proteins that they can bind to that doesn't really matter. But there are some proteins that they bind to that are wicked critical, like a voltage-gated sodium channel. The nervous system ain't gonna work if you can't open a voltage-gated sodium channel. Nothing works, okay? And at the end of the day, if you can't get your diaphragm to contract, you'll die, okay? The critical thing here is if your nervous system shuts down, okay, so cognitive thought might go away, but if you can't send an action potential to your diaphragm to breathe, then you've only got about 3 minutes, okay? So really critical in terms of nervous system. One of the real critical nerves is the nerve contracting the diaphragm, because we have to keep that up and running or else the whole system is gone, right? So binding, if we have a lot of hydrogen ions and binding them to negatively charged proteins and they can no longer function, we start to mess with our foundational systems. But the opposite is also true. We also have proteins that change their shape because a hydrogen ion is bound to a negative spot. And then when we start to decrease our hydrogen ion concentration, we will strip those off. And if we strip those off, that protein can no longer change the shape that it needs to critically function, right? So all enzymes are all shape changes. Transporters on membranes, all because of shape changes, okay? So we are hugely susceptible to the shape of our proteins. Hydrogen ions mess with that. That's why that's why free radicals are such a big deal too. Free radicals do exactly the same thing, right? They bind to where they're not supposed to bind, and suddenly we can no longer function like we were. So we are wicked sensitive to hydrogen ion. Critical though, it's the free hydrogen ion we got to take care of. If we can bind that hydrogen ion to something else, keep it busy over there, we're good to go. Okay? So really it seems to be all about keeping the free hydrogen ion bound to something that doesn't matter so much to keep it from binding something that does. Okay, so that's kind of the game afoot. All right, so where do we produce, how do we get hydrogen ion into the system? Essentially, where is hydrogen ion coming from? So we have volatile and non-volatile. Okay, so volatile, it's in the form of CO2, right? So this is through cellular metabolism. Or cellular respiration. Okay, so aerobic metabolism is going to produce CO2. Okay, and we know that that CO2 I like this equation almost as much as flow equals delta P over R. You'll learn that because we're going to write it out about 14,000 times before the end of the course. So if I were to increase my CO2, indeed I have the ability to liberate hydrogen ion from that carbonic acid. Okay? We make massive amounts of this in a day. Every cell is making CO2. You have trillions of cells. Okay? We make this to the tune of 13,000 millimolar per day. We have a massive hydrogen ion load to handle. We're making 13,000 millimolar per day, and we have to manage it to 40 nanomolar. Okay? So we have this is an incredible task for the body to do. So we have that source of just cellular respiration, but then there's also non-volatile sources. So this is a lot of the biochemical stuff, like catabolism of proteins. Anaerobic metabolism is going to result in hydrogen ion production. So classic lactic acid production due to anaerobic metabolism. You can bring all kinds of acids in your diet depending on what you're bringing in on a daily basis. Right? If you drink a lot of Diet Coke, that's very acidic, so you're increasing that acid load per day. So this load is a little bit less than our respiratory, or than our cellular respiration load, but it's still in terms of millimoles per day. So 50 to 70 millimoles per day. So we're making things at the level of 10 to the minus 3 millimolar and having to regulate it around 10 to the minus 9. So we have got to be good. We've got to be good at this. Okay, so then let's look at the three ways that we have to try to handle this load while regulating it within a nanomolar range. So we have 3 lines of defense for this. Where's my thing here? First we have, so this is in terms of the regulation. Hydrogen ion, how are we going to do it? We have buffers. We have buffers and lots of them. So buffers are going to work for us on a very immediate time scale, a milliseconds to seconds time scale. So as we produce it, we have buffer nearby that we can bind that hydrogen ion and essentially hide it. That's what buffers do. They can bind hydrogen ion, and that must not change their function, right? So it's safe to hide the hydrogen ion there. And what it's going to do, though, is minimize the disturbance, because the body didn't get rid of it. The body just hid it. In order to fix any problem, you have to get rid of the hydrogen ion from the body, right? If it's still in the body, regardless of even whether you've hidden it in the form of water or you've hidden it in the form of another buffer, you've just hidden it for the time being, okay? So what we do is we bind, essentially this strategy is to bind hydrogen ion so it doesn't bind anything else, so that we can minimize a disturbance. So we have specific buffers in specific compartments in the body. Not all buffers are all places. Okay, so for instance, if we look at the cellular level, inside a cell, we will have proteins that can bind that hydrogen ion, and obviously it's not going to change their behavior, so it's okay to bind them to these. Okay, so we have proteins that can bind hydrogen ion, we have bicarb that can bind hydrogen ion, and we have phosphate buffers. So if we look, and those are all inside the cell, so if we look at these, we just essentially have a set of proteins that can bind our hydrogen ion. Okay, we have phosphate. So we have HPO4, -2. That's it, okay? So we have phosphate sitting there that can also accept a hydrogen ion, and we have that bicarb that we've been alluding to. Okay, so these three that can accept the hydrogen ion, obviously without causing any issues. Inside the cell, the three are present, and there's also that carbonic anhydrase. And remember that carbonic anhydrase was speeding up the carbonic acid reaction. Okay, we saw that when we looked at the blood and how oxygen and CO2 are carried in the blood. We talked about the carbonic anhydrase there and how it can effectively speed up the reaction. So inside the cell, we've got all those tools. Outside of the cell, so interstitial space, we have carbonic anhydrase that's normally, it's bound to cell membranes, but it is exposed to the outside. The interstitial space is exposed to the activity of the carbonic anhydrase, so we do have our bicarb buffer, and then we can speed up that reaction based on the presence of the enzyme. And we have phosphate out in this interstitial space, but very few proteins, right? We talked about that when it came to fluid flux, right? That there wasn't a whole lot of proteins that we would find in the interstitial space. So a little less buffering power in our interstitial space. In our blood space, think about our blood compartment. There are two compartments within the blood compartment, right? There's the plasma compartment and there's the red blood cell. Okay, and they each have different tools. The plasma has, like the cells, have proteins, bicarb, and phosphate, but no carbonic anhydrase. So the carbonic acid equation, a little bit, or shifting is a little bit slower up here. And our red blood cell has everything that other cells have in them, proteins, bicarb, and phosphate. Bicarb with that carbonic anhydrase, and in particular we saw how that one of those proteins in particular was hemoglobin, and how the hemoglobin bound to hydrogen ions. So if you go back and look at those equations again, you'll see how that red blood cell is very specifically has hemoglobin and how it's handling hydrogen ion, whether it's bound to oxygen or not. Okay, so it is helping out. Helping us out with binding that free hydrogen ion. So we have different capacities here, like so in terms of whole body capacity, we have about 8 millimolar protein and phosphate that acts as a buffer for us. Okay, and when it comes to bicarb, that's where most of our action is. We have about 24 millimolar. Okay, so we've got lots of bicarb capacity, a little bit of protein and phosphate. Okay, and they're definitely distributed slightly differently in the cells. Okay, so that's our first line of defense, and the reason they talk about it as our first line of defense is because it's the fastest, milliseconds to seconds. So the millisecond you start having a free hydrogen ion problem is the millisecond you start fixing it. You start minimizing the disturbance. Okay, you start hiding it, right? Because the moment that I have a lot of free hydrogen ion, I'm going to push the equation in this direction. Right, it's all mass action. I'm going to push the phosphate equation in that direction and the bicarb equation in that direction. Okay? All right, we'll stop there for today and we'll head on into the lungs and the kidney on Thursday.